Okay, how's everybody doing this morning? Good, good. Tuesday, yeah, it's we're still getting started. All right, so I wanted to start today with a quick reminder that this Thursday we will be having our field trip to the Old Folsom Powerhouse. Okay, so we will not have class on Thursday. So please plan to meet at the Old Folsom Powerhouse at 9:45 in the morning. So this flyer is up on Canvas on the announcements page. You can take a look. It has the time and the address there. So we'll meet at 9:45. The tour will start at 10 and it will run to 11:30. Okay? So I like to meet a few minutes early just to give you time to find parking and find the place and make sure that we're all there and ready when the tour is ready to begin. Okay? So there's a map here that shows you how to get to the facility. So this is Greenback Lane there. That you'll probably come in on Greenback Lane if you're coming from this part of the world. So you'll come down on Greenback. The Old Folsom Powerhouse is here. You want to drive past that, and then at the next light, you'll take a left and you can park in this parking lot here. The reason is that this parking lot here is free. You can park there all day, it doesn't cost a dime. There's a parking lot at the Powerhouse, but it costs $10 to park there, okay? So I highly recommend that you skip the Powerhouse parking lot, you park right here on the corner, and then you just walk back about a block, and we'll meet at the Powerhouse around 9:45, okay? So this should be a beautiful tour. I think the weather's gonna be nice. There are some things that I recommend that you bring. So layers of clothing is a good idea. Just, you never know if it's gonna be cool in the morning. Sometimes it's cool when we get there and then the sun comes out and it warms up. So layers are always good. You can bring a hat, an umbrella if it looks like rain. You can bring a bottle of water, and definitely a camera if you like to take pictures, because there's some really cool stuff there. I think I mentioned earlier that they have some really awesome old-time machinery, some really cool-looking facilities. So definitely bring a camera if you want. You can also bring lunch or a snack, because the Powerhouse is right on the American River here. And it's a beautiful area. They have picnic benches, and the tour is going to run until about 11:30. So if you don't have any class right afterwards, this is a great place to have a little picnic lunch, sit out with nature, and see the river go by. So it's just beautiful. You can definitely take advantage of that. The only thing that you should not bring are family and friends. Okay, this tour is specifically for people in this class, and we're not allowed to bring other people along just for liability reasons. That being said, if you like the tour, you are welcome to go back. This is a state historic park. It's open all year round, and there's no admission charge. So you can, if you like the tour, you can come back and bring your friends and show them around. You just can't bring them on this particular field trip. Okay. So again, that's this Thursday, 9:45. You are responsible for getting yourselves there. You can drive yourself there, or you can carpool, take public transportation. But we want to meet there. We're not going to have class here. If you show up at this building, nobody is going to be here, okay? So you need to go there. So are there any questions about that?
I know.
Yeah.
Are we allowed to bring our lunch with us?
Yeah.
You're not gonna say, drop your lunch here or something?
No, I don't think we're going to be walking around for about an hour and a half, so I don't know if you want to carry the bag the whole time, but I don't think they've ever, had a problem with this. Yeah.
I would just say, for those that don't know, Madison turns into Greenback as you get to Folsom.
Yeah,
So don't go up to Greenback and then down. You can just take Madison all the way out.
there you go. Yeah. Yeah. The field trip is not mandatory, but it is highly recommended, and you will get extra credit if you show up, okay? So if for some reason you can't be there, that's all right, but I highly recommend it, and there will be extra credit. So, all right, so that is the field trip. Oh, the last thing, many of you have filled out the waivers online, but some of you have not yet. So please make sure you do that. Make sure you fill those out. Again, you can find a link to the waiver from Canvas. So if we're on the Canvas page here, so this is the announcement, and you can find a link to the waiver there, and then you can download the waiver and fill it out. It looks very much like the main waiver for this class, but it's specifically for the Folsom Powerhouse field trip. So you need to fill this out even if you have filled out the one for the class. And you need to make sure you do this by Thursday, because if you don't have this filled out, you cannot come on the field trip, okay? So please make sure you fill that out. You can upload it to Canvas, or you can turn in a hard copy. That's fine too. So any questions about that? All right. Then let's go on and talk about our lesson for today. So we're going to start with a brief review of voltage and current in series circuits. We talked about this a couple of lectures ago. We're going to review that. Then we'll go and we'll talk a little bit about parallel resistance. We covered this last time. So we looked at how we could figure out the resistance of a parallel circuit when all of the resistors were the same, and also how we could figure out the equivalent resistance when we have different resistor values in that circuit. So we'll talk about that. And then we'll go on to our main topic, which is current and voltage in parallel circuits. So we'll say why we care about that. We'll do an example and figure out the current and voltage in a parallel circuit. And then we'll compare the voltage and current in parallel circuits versus series circuits. Okay? So I don't think that this is going to take too long. I know that some people, the lab last time lasted a little bit longer than usual, so some people weren't able to finish. So I think this lecture should be a little bit shorter. You should have a little bit of extra time to work on your labs today. So hopefully be able to finish up the last one and then do the lab for today as well. And we'll do a preview of that lab at the end of the lecture. So any questions before we get going? Cool. All right. So let's review voltage and current in series circuits. So remember, we said that a series circuit looks something like this. You could have a power supply and then two or more resistors connected so that the end of one resistor was connected to the beginning of the next. So in series, we said that all of the current that flows out of one resistor has to flow directly into the next one, right? So the current for one resistor, is that the same or different than the current for other resistors? The same. So in series circuits, the current is always the same for all of the components, but what about the voltage? Does the voltage across this resistor have to be the same as the voltage across that one? No. So the voltage may be different. Okay. So,
I thought it dropped, or does it do it all the time? I guess?
well, so yeah, the voltage changes from one part of the circuit to another. There's always a voltage drop from the one side of the power supply to the other, but the voltage across each resistor might be different. So if we have 5 volts over here, we might have 3 volts here and 2 volts there, for instance. These voltages don't have to be the same values as each other. So, yeah, great question. Other questions? Okay. So then, last time we talked about parallel resistance. We said that if we have several resistors in parallel, like this, we could find their equivalent resistance. In other words, if we put a meter from one side of the circuit there to the other side, and we measured it, we would see some resistance value, and we could use a formula to calculate what that resistance value would be. So if all of these, let's say that all of these resistor values are the same. So that one is 600 ohms, this one is 600 ohms also, and the last one is 600 ohms. When we have the same resistor value for each of the resistors, how do we calculate the equivalent resistance? Yeah.
You take the 600, you divide it by how many resistors there are.
Exactly. We take the 600 ohms and divide it by the number of resistors. So in this case, that's 600 ohms divided by 3 resistors. So what does that give us? 200 ohms. So those 3 resistors in parallel act like a single 200 ohm resistor. So that's how we can find this value when all of the resistors are the same. Okay. Any questions about that?
Oh, why?
Why? Yeah. Well, because remember we said that when we have parallel resistors, they give the electricity more paths to flow down. So when you have, if you had just one single resistor, all the electricity would have to flow through there. And it would be kind of difficult for the electricity to move. But when you add more resistors, you're giving the electricity more paths to take, and you end up with less resistance overall.
That makes sense because it splits it between 3 paths. But
Right.
so they're acting as 200 ohm resistors, but they could hold up to 600.
No. So the equivalent resistance of the whole circuit is 200 ohms.
Okay.
But the value of each individual resistor is 600 ohms.
Is that just in case like 2 of them were to like stop working, you would still be able to?
Well, so this could represent various kinds of circuits in the real world. So if you had more modern holiday lights, for instance, each one of those is like a little incandescent bulb, and each one has its own resistor value. So
So if one goes out, they don't all go out.
right, exactly.
Okay. So
Yeah.
it's kind of like so if one of the resistors go out, the other 2 can act as backup and carry the dead weight in a way.
Well, it's just a model for certain types of circuits.
Okay.
Yeah. Yeah. Other questions? All right. So that's how we can figure out the resistance for a parallel circuit when all of the values are the same. when we have different resistor values, we had to use another formula. So let's say we have two resistors in parallel, but now one of them has a value of 250 ohms, and the other one has a value of 1,000 ohms. Can we just divide one of these by 2 since there are two resistors? No, we have to use this other formula. So the other formula is R total equals 1 over R1 plus 1 over R2. And if you had more resistors, you could keep going. So 1 over R3 plus, on and on until you get all of the resistors that you have in your circuit. So in this case, R total equals 1 over, and then 1 over 250 plus 1 over 1,000. So what is 1 over 250? Anybody have a calculator out there? Pardon me. Oh, pardon me.
1 over.
What? I don't think it's 0.25. I think it's maybe 0.0.
0.004.
Okay, perfect. Plus 1 over 1,000 is 0.001. So this is 1 over 0.005. So what does that come out to be? Anybody do that on a calculator?
200.
200. All right. So the equivalent resistance here is 200 ohms. So in other words, if you took a meter and you measured the resistance from up here to down there, you would see a value of 200 ohms. Okay? So that's how we calculated resistance in a parallel circuit when the resistor values are different. They're not the same as each other. So any questions about that? The key thing to remember is that in a parallel circuit, the total resistance is always less than the smallest resistor in that circuit. So it doesn't matter if the resistor values are the same or different, the equivalent resistance will always be less than the smallest value. So in this case, the smallest resistor is 250, so our equivalent resistance better be less than that. And sure enough, it is. Okay? All right. So then let's go on to our main topic, which is current and voltage in a parallel circuit. So why do we care about current and voltage in a parallel circuit? Well, many circuits in the real world contain parallel elements, and we might want to be able to figure out their voltage or current. So this helps us to understand that circuits that other people have designed, helps us to understand how they work, and it also helps us to design our own circuits. Okay? So it just helps us to see what's going on inside of these circuits. So let's do an example. So let's say that we had a circuit with these resistor values, and a power supply. And let's say that this power supply is giving us 10 volts. So we want to know we'll call this resistor R1, this resistor is R2. We want to figure out the voltage and the current for R1 and the voltage and the current for R2. And we also want to know the total voltage and current for the whole circuit as well. So let's write this down. We want to figure out the total voltage, V total, the total current, and the total resistance, and then the voltage for R1, the current for R1, and then the voltage and the current for R2. So we want to know all of these things. So let's try and figure out what they are. So the total voltage is the voltage that's coming from the power supply. So do we have to do any calculations to figure that out? No. So that's just 10 volts. We can read that right off of the schematic. So 10 volts. Do we know the total current yet? No. So we might have to come back to that. What about the total resistance for this circuit? That's the equivalent resistance for all of the resistors that are in the circuit. Yeah, we calculated that already. That's the 200 ohms. So we can write that down. So that's 200 ohms. Now, this is the total equivalent resistance for the circuit. So we could say that the whole circuit is acting like this. We still got the 10 volt power supply, but now we just have an equivalent resistance over here of 200 ohms. Okay? So we can look at this circuit and we can redraw it like that. Now we have a circuit and we know the voltage for the circuit and the resistance for the circuit. Can we calculate the current if we know the voltage and the resistance? Yeah, and what law do we use for that? Ohm's law, perfect. So we remember Ohm's law is like this, V, I, and R. We're trying to figure out the current here, so we write down I equals, we cover that up, we see it's V over R. So in this case, that's 10 volts over 200 ohms. So that comes out to be 0.05 amps. And if we convert that to milliamps, that would be 50 milliamps. So that's the total current for the whole circuit. So that's the current that's flowing out of this power supply. And it's also the current that's flowing through this resistor. So we can write that down. That's our total current. So that's 50 milliamps. Does anybody have questions about how we figured that out? Yeah.
Well, not about how you figured it out.
Sure.
But, you always wanted to convert to milliamps, or can we keep it amps as well?
You can keep it in amps or milliamps. It's fine either way.
Okay.
Yeah. When you're filling in a quiz online, it might specify the units. And in that case, you would have to convert it to whatever units it said. But if you're just writing it out on paper, I don't care. Yeah. Yeah, other questions? All right. So now we want to figure out the voltage and the current for the other resistors. Well, there's one key fact to remember here that can be very helpful, and that is that voltage is the same at every point on a wire. Okay? This can be very helpful when we're looking at any circuit, and especially parallel circuits. Let me show you how. So we can call this point of the circuit ground. Anybody remember what that means? What is the voltage at ground? 0 volts, exactly. So we have 0 volts there. Now we said that the voltage is the same at every point on a wire. So this line represents a wire. So what would be the voltage at that point right there? 0 volts, because it's connected by a wire over here, and we know the voltage there is 0 volts. The voltage is the same at every point on a wire, so the voltage there is 0 volts also. What's the voltage right there? 0 volts, exactly. It's still on the same wire, still the same voltage, 0 volts. What about right there? What's the voltage there? 0 volts, still the same wire, right? Still, there's no component in between here and there. It's all one continuous wire, so it's still 0 volts. What about over there? 0 volts. Okay, so all along this wire, the voltage is 0 volts, every point along that wire. Does that make sense? Yeah.
I'm just a little confused because I thought earlier you were talking about the voltage being different at different points along the circuit.
It is at different points along the circuit, but not at different points along a wire. So on any wire, the voltage is constant.
Oh, okay.
But at other points, and we'll see this in just a second, at other points in the circuit, the voltage will be different.
Oh, interesting.
Yeah. Yeah.
So is the voltage 0 there because it's the negative side that's connected directly to the ground?
Well, it's 0 because we called this point ground, and we have essentially, when we do that, we're just defining that point to be 0 volts. That's what ground means in these circuits. When we put a ground symbol there, it just means that we're calling that voltage 0 volts. So we put the symbol there, and we said, therefore, that point is 0 volts. So every other voltage along that whole wire is 0 volts as well. Yeah. Other questions? All right. Yeah.
Because you said that's 0 because we said it's 0, but that's only 0 because it's not connected to a power source. Is that what you're trying? Because you said because we said it's 0, so how do we just say it's 0?
Well, we can pick the voltage at. Well, basically, voltages are always a difference between 2 points. So we can specify the voltage at one point on the circuit, and then we can define everything else relative to that. So oftentimes we just pick one point and call that 0, and then the circuit tells us what the voltage will be at every other point relative to there. It's kind of like when we're talking about heights in the real world. If you want to know the altitude of, say, a town, say we're talking about Tahoe, that's at like 7,000 feet, right? But it's 7,000 feet relative to something. We have to pick the 0 point. So oftentimes we pick the 0 point to be sea level, but that's kind of arbitrary. We could have picked it to be the very bottom of the ocean, right? Or we could have picked it to be, our hometown. we just have to pick some point, and then we can measure everything else relative to that. So in circuits, we pick some point to be 0 volts, then we can make other measurements relative to that. Yeah.
So it doesn't necessarily mean it measures as 0 at that point, it just means that we're calling that 0?
Well, remember, voltage is always a difference between 2 points. So when we say that that's 0 volts, we would put our basically we can use that as a reference when we're making other measurements. So we would put one probe of our meter there, and then another probe at another point in our circuit, and we can make measurements relative to that point. But yeah, if we put both of our probes at that point, we would see 0 volts because there's no difference between them. Yeah.
Oh, yeah, I see what you're saying.
Yeah. So this. All right. So this is 0 volts there. And now we have our power supply here. And that power supply is a 10 volt supply. That means that there's a 10 volt difference from one side of the supply to the other. So if we know that one side of the power supply is at 0 volts, what will be the voltage at the other side of the power supply? 10 volts, exactly. So we have 10 volts right there. So if we put one lead of our meter down here and the other lead up there, we would measure 10 volts. Yeah. So what does that mean about the voltage at that point? What's that voltage going to be?
10 volts.
10 volts, yeah. Yeah.
So if we took the meter and measured 2 points on the wire for the top wire, it would say 0 volts because there's no difference in between them, even though that's like the top of the power supply.
That's right. If we measured the difference between here and here, say, yeah, the meter would tell us 0 volts. There's no difference between those 2 points. Yeah. Yeah. So when we say that this is 10 volts at a point, what we're really implying is that there's a 10 volt difference between that point and whatever we're calling ground. Okay? All right, so that's 10 volts up there. What about over there? What's that voltage there? 10 volts, perfect. And so what about the voltage right there? 10 volts, exactly. And what about the voltage right there? 10 volts, perfect. Okay, cool. So now our question is asking, what is the voltage across resistor 1? So in other words, what is the voltage difference between one side of resistor 1 and the other? So can anybody look at this resistor, tell me what the difference would be from one side to the other? 10 volts, exactly, because we have 10 volts on one side and 0 volts on the other. The difference, 10 minus 0, is 10. So we have 10 volts across resistor 1. What about across resistor 2? 10 volts, exactly. So we can write those in. The voltage across resistor 1 is 10 volts, and across resistor 2 is also 10 volts. Okay? So anybody have questions about how we got that? Yeah.
So the only time it would not be like, say in this example, 10 to 0, would be if the resistors were parallel, because then it would be a voltage change across both of them instead of just across one.
If they're like this, they're series. I think that's what you meant.
Yeah. I'm just saying, if they're in series, that's the only time it would be different from going to 10 to 0. Because this here, you're going from 10 to 0, but there you would be going from like 10 to 5 to 5 to 0.
Right, exactly. So, yeah, so that's a great observation. You can, in a parallel circuit like this, the one side of the power supply is always connected to the top of every resistor. So the top of every resistor is going to be at the power supply voltage. The bottom of every resistor will be connected to the negative side of the power supply, so that will be at ground. So the voltage across every resistor in parallel will be the same. Yeah, and yeah, we're going to emphasize that in just a second. So yeah, that's a great observation. Yeah.
We measure the current. It is 50 milliampere on the top of the wire.
Yes, right. Thank you. So that's right. So over here we said that there's 50 milliamps coming out. So also over here.
At the same time, in the two side of the wire, because the voltage is the same, there is no difference between the voltage. So how this current is possible?
I'm glad you asked. So we know the total current for this circuit, and we know the voltages are the same for these two resistors. So are the currents going to be the same for those resistors? Anybody want to guess? No, because they're different resistor values. So even though the voltage is the same across them, it's going to be harder for the electricity to flow through the bigger resistor and easier for it to flow through the smaller resistor. So more of it is going to flow this way. And can we figure out how much is going to flow in each direction?
Yes.
Yeah, we can use what law for that? Ohm's law, perfect. So before we do that though, I did want to write down your observation over here, which is that, so in parallel, the voltage is the same for all of the resistors. But we just said, what about the current? Does the current have to be the same? No. So, but current might be different. So that's kind of the opposite of what we have in series. In series, the current is always the same, but the voltage might be different. In parallel, the voltage is always the same, but the current might be different. It's this sort of these opposites. It's kind of cool, I think. So anyway, let's get back to our problem here and figure out what that current actually is. So,
and when you say current, are we trying to measure what ohms each one has?
no,
Amps.
yeah, amps. That's right. So we want to figure out how many amps or milliamps are flowing this way through R1 and how many milliamps are flowing this way through R2. So let's look at R1 first. So we've got the current is voltage over resistance. So for R1, what is the voltage going to be? Yep. So it's 10 volts across R1. So that's 10 volts over, what is the resistance for R1? Yep, 250 ohms. So, so what does that come out to be? 0.04 amps. And so how many milliamps would that be? 40, exactly. So we have 40 milliamps flowing that way. Now, we could do the same thing to figure out the voltage, or the current through R2, but there's another way to think about it also. Yeah?
I was just about to say there's a shortcut since there's 50 milliamps flowing through the whole circuit.
Right.
There can only be 10 amps on the other, or 10 milliamps on the other side.
Exactly. We have 50 milliamps flowing that way, so therefore there must be 50 milliamps coming in there. And now it gets to this junction and it splits. So some of it goes to the right, some of it goes to the left, but altogether it has to add up to this same number, 50 milliamps. It's like if we had 50 gallons of water coming down a pipe and 40 gallons went one side, the rest of it would have to go to the other side. So how much does that leave coming this way? Yeah, 10 milliamps going that way.
Isn't it just taking the lowest value too and just comparing it to every other one? Like, can't you just do like, I don't know, like R1 is 40, so it's just 40 times 250 over 1,000, and then technically be 10. It's just kind of the ratio, isn't it?
Yeah, I mean,
Being multiplied by?
so 40 times 250 would give you the voltage across this, and then dividing by 1,000 would be like V over I, so that's, yeah, Ohm's law again. So we've got 40 milliamps that way and 10 milliamps going that way. So we can fill in those answers over here. IR1 is 40 milliamps, and IR2 is 10 milliamps. Okay? And now let's look at what happens to these currents at the bottom here. Down here, we have 40 milliamps flowing in from this side, and we have 10 milliamps flowing in from that side, and they combine together. So how much current do we have flowing out this wire here? 50 milliamps, exactly, perfect. And that's good because that's flowing back into our power supply, and we know that the current going into the power supply had better be the same as the current coming out. It always is. So that shows us that our math worked out correctly, okay? So that's how we can figure out the voltage and current in a parallel circuit. Is there any questions about that? Okay, cool. All right, so we'll have a chance to practice with that more as we go on through the semester, but that's the basic idea. So what we can do when we analyze a parallel circuit is we can find the equivalent resistance and then use that to find the total current for the circuit. And then when we look at our resistors, we know that the voltage across each resistor is always going to be the same as the total voltage in a parallel circuit, because the top of the power supply is connected to the top of the resistors, the bottom of the power supply is connected to the bottom of the resistors. So the voltages will be the same as the power supply, and then we can use those voltages with Ohm's law to find the current for each resistor. So that's the general procedure. So, all right. So we talked about why we care about that. We did an example circuit here, and we've compared voltage and current in parallel circuits versus series circuits. So we have this kind of symmetry going on, where the current is the same in series, but the voltage may be different, and it's the opposite in parallel circuits. So it's pretty cool. So that's what I wanted to talk about today in our main lecture. Are there any questions about that? All right, so then let's go on and let's do the preview of today's lab.
That was also our today's lecture as well.
Yeah, that was today's lecture. So, yeah, last time we talked about just the resistance in parallel circuits.
Dang, this is the longest review. I was like, I like it.
Woo!
I was in here, so I was like,
Yeah.
But I was like, dang. Okay.
No, right. So last time we just talked about resistance. Today we talked about voltage and current in parallel circuits. Yeah. Life moves pretty fast sometimes. Don't stop and look around, you might miss it. All right. Okay. So this is the lab for today. So in today's lab, you're going to be doing hands-on work. So last time we just did multisim. Today we're just going to be doing hands-on stuff. So the first thing that the lab says to do is to wire a circuit according to the schematic here. So can you see the wires on the schematic there a little bit? All right. So is this circuit in series or in parallel? Series, yeah. So you're going to wire this up on a breadboard. One way to wire up resistors in series is like this. So you can have your power supply connected to these red and black wires over here, and then you have your resistors connected end to end, so that the end of one resistor is connected to the beginning of the next. Okay? So those resistors are in series. Now, the first thing that the book says to do is to measure the resistance of each individual resistor. In order to do that, you want to take the resistor out of the board and measure it by itself in the meter. You don't want to ever measure resistance while the resistor is connected in a board. You don't want to measure an individual resistor that value that way, because the other components in the circuit may affect the resistance measurement, okay? So when you're doing this, you take the resistor out of the board, you measure its individual resistance, and you write down your reading with as much precision as the meter provides. So if it says, 7.43 kilo ohms, you don't round that up, you just write 7.43 kilo ohms, okay? That way you get as much precision as possible, and that will help you with your calculations. And then the total resistance, you can measure the total resistance by making sure that this is disconnected from the power supply, and then measuring the resistance from the red jumper wire to the black jumper wire. Okay? But make sure it's disconnected from the power supply first. And you measure that resistance there. That'll be your total resistance. So questions about that? Yeah?
Couldn't you also just flip one of the meter from the top to the
Yeah, so electrically that would work. Practically it presents some problems, because if you clip on here and then you bump the wire, it just pops out very easily. So it's electrically it would work, but it's prone to errors, so I wouldn't recommend it. Yeah, other questions? Yeah.
When we calculate theoretical resistance of the circuit, should we use theoretical values of resistors or the actual values?
Use the actual measured values, because if you use those actual measured values, then any calculations that you do should match up more closely with any measurements that you make. So if you, for instance, if you measure the total resistance and then measure the total voltage, and then use Ohm's law with that, it should come out very close to the total measured current. Whereas if you used theoretical values for resistance that weren't quite the same as your actual values, and theoretical values for voltage, then your calculation answer might not match up as closely with your measured answer. Yeah. Okay, so you measure the individual resistors and then the total resistance, and then next you want to measure the voltages across each of your resistors. So you measure the voltage across each one. Now remember, is voltage measurement a destructive measurement or a non-destructive measurement? Non-destructive, right. So you don't have to take the circuit apart in any way in order to make these voltage measurements. What you can do, you can touch the edges of the resistor like that, but again, that's prone to error. So what I like to do is I like to clip a wire into each of the leads of my meter and then just plug those jumper wires in to the rows at the ends of my resistor. That makes a good electrical connection. It's not going to pull the resistor out of the board, and it makes it easy to just read the value right off your meter. Okay? So you can measure the voltage across each of the resistors that way, and then you can measure the total voltage. That's the voltage from one side of the circuit to the other. So you can do that by by putting one lead in one side of the circuit and the other lead in the other side, like that, and then measuring that voltage there. So that's your total voltage. Questions about that? All right. And then the next part of the lab is to calculate the current, the total current for that circuit. So that's where you would use your measured resistance and your measured voltage, and you'd use Ohm's law to calculate the total current. So you'd write in your calculated value there, and then you want to measure the current for your circuit. So this asks you to measure the current through R1. Now, is current measurement a destructive measurement or a non-destructive measurement? Destructive. So you have to partially deconstruct your circuit in order to make that measurement. So remember, we've got a circuit like this. We got our power supply, and then our 3 resistors. If we want to measure the current through resistor 1 here, we have to break the circuit apart right before resistor 1, and that leaves us with 2 loose ends of the circuit. And then we have to connect those 2 loose ends of the circuit to our 2 leads from our meter. So that way, any current that was flowing through that part of the circuit now has to flow through our meter and get measured, and then continue on through the rest of the circuit. Okay? So this is what we have to do in order to measure the current. So when we're doing that on our board, if we want to break the circuit apart right before one of those resistors, what we can do is we can just pull a resistor leg out of the board. So we've broken the circuit apart, and now the circuit has 2 loose ends. One of the loose ends is pretty easy to see. Can anybody see one loose end of the circuit? Yeah, that resistor leg that's just hanging out in space. So that's one loose end, so we'll connect that to one of our meter leads. Now, the other loose end of the circuit is harder to see. Can anybody tell me what the other loose end of the circuit would be? Not quite. These are going to be connected to your power supply.
Where the resistor was originally plugged in at.
Exactly, where that resistor used to be connected. Just like up here, the resistor used to be connected there, that's our loose end. Here it's where our resistor used to be connected. On the board, that's just a hole. So that's why it's so hard to see, because it looks like all the other holes. But where that resistor used to be connected is the other loose end. So what we can do is we can put a wire in where that resistor used to be connected. Now it's kind of easier to see that as the other loose end of the circuit. If that end of the wire was connected to that end of the resistor, we'd kind of be back to where we started. So anyway, these are the 2 loose ends of our circuit. We connect those 2 loose ends to the 2 leads of our meter. We put the meter in current mode, and now all of the current flows through our meter and then back into the rest of the circuit. So that's how we measure current through a resistor. Okay? And then when we're done, we take the meter off and we put the circuit back the way it started out. And we do that before we make any other measurements. That way, we know that we're back to a good known state for our circuit and everything is right. And then we can start making other measurements. If we try to make, just connect things before we put everything back, we're likely to make mistakes and have the circuit go wrong. So you always want to put everything back to its starting condition before you start making other measurements. Okay? So that's how we can make the current measurements for our circuit. So we want to measure the current through R1, R2, R3, and then the total current. So the total current is the current that comes out of our power supply. So again, we have to break the circuit apart in order to make that measurement. Where could we break the circuit apart in order to measure the total current? Yeah.
Beginning and end.
Yeah, exactly, at the beginning or the end. So up here, the beginning of the circuit is right where the wire comes in from the power supply. So we could break the circuit apart there, and then that would be one loose end of our circuit. We could connect that to one lead of our power supply. The other loose end would be where that wire was connected. So those would be the two loose ends of our circuit. We could connect those two loose ends to our meter and then measure the total current that way. Okay? So that's how we measure total current. Any questions about that? All right, so then when we're all done, we put everything back and we're all set.
Hold on a second.
Yeah.
How do you do the total current again?
So the total current is the current coming out of the power supply. So in order to measure that, we break the circuit apart where the current comes from the power supply. So that's that the current is coming down this red wire from the power supply. So we break the circuit apart right at that point where this wire attaches to the breadboard. So we break that apart. This wire would be one loose end of our circuit at that point, and then we can attach a jumper where this wire used to be connected. That'll be the other loose end of our circuit. And then we attach our meter between those two loose ends. Right, and that's it. All right. So then the second part of our lab relates to this parallel circuit. So here we're using the same three resistors, but now they're connected in parallel. So this is a way that you could make a circuit with three resistors in parallel. You just have them all connected so that the tops of the resistors are all in one row and the bottoms of the resistors are all in a row. Okay. Now, here it asks for the calculated resistance. So you would use the individual resistor values that you measured before and the parallel resistance formula to calculate that. Then the measured resistance you can find by, again, making sure this is disconnected from any power supply and then connecting these two loose ends to the meter and measuring the total resistance that way. Okay? So that's the measured resistance. And then Then you measure the voltage across each resistor. So again, you measure voltage just the way that I showed you before, but now you measure on this parallel circuit. And then finally, you measure the current, and you calculate the current for each resistor. You measure the current for each resistor, and then you measure and calculate the total current as well. And that's the lab for today. So any questions about that? All right, then I will take attendance and then I'll let you go.